Power amplifiers, they are basically large signal amplifiers, right? So far, whatever we have studied, say common source, common gate with respect to MOSFETs, BJTs, and even with respect to op-amps, they're all small signal amplifiers, right? They take the input of some signal which are in a few milliohms or microvolts, and then they amplify the signal in terms of voltage and then give the output. But these amplifiers, power amplifiers, they are large signal amplifiers. Basically, once you have a cascade of many amplifiers, right? Just one amplifier cannot amplify the signal to a greater extent, correct? So generally you will have a cascade of many amplifiers, and at the end of every stage, okay, there is a power amplifier which is actually driving the load. Like, for example, it could be an audio amplifier, or it could be a loudspeaker, it could be a motor, right? So just before the load, you will have a power amplifier in order to drive that load. Okay, so these loads which are present at the end, basically they have very low resistance. Okay, and therefore, and they need large power to drive that load. So that's why it's called as power amplifiers. So an important parameter here is not gain. Okay, just like in voltage amplifiers, small signal amplifiers that we've studied so far, we said, voltage gain, input impedance, output impedance every time. But here, one of the important parameter in the power amplifier is what? I think you've done this experiment. No? Can you tell me what did you calculate in power amplifiers? What's the important parameter in a power amplifier?
Efficiency.
Correct. So basically, it is efficiency, which is denoted by eta, right? So how efficiently you can convert the DC power, that is VCC, what you give in case of all power amplifiers, how efficiently that can be converted to AC power. So power efficiency is how efficiently a DC power can be converted to AC power. That's what we are basically trying to analyze in all power amplifiers. That's the most important parameter. Okay, now let's consider a simple amplifier. So, let me call this is RB and this is RC. So this is VCC. And what amplifier is this?
Common emitter.
Yeah, so this is a simple common emitter amplifier, and the same signal, the same circuit can be used for large signal amplification also. Okay, so this is called as a class A power amplifier. There are several types of power amplifiers, okay? Class A amplifier, Class B amplifier, Class AB amplifier, Class C amplifier. We'll see all that one by one. We'll also discuss the advantages and the disadvantages of all the amplifiers that are there in a syllabus. So this Class A amplifier, as you can see, the transistor is always biased in the active region, right? Which means the transistor is always on, whether you have a signal at the input to be amplified or not, this is always on. This is never off. So, I mean, intuitively, you can say since this transistor is always on, the efficiency of this is also quite less, which is correct. Okay, so the efficiency of this is also quite less because this is always on. So it's something like you have a mobile, irrespective of whether you're using that mobile or not, the battery keeps discharging. It's something like that. But you do not want that to happen, right? Correct? So this is something like that. It's a similar example. So the efficiency of this is less, but this is, and therefore it's very hardly used because it's always on. But then since it's a part of your syllabus and we need to study all kinds of amplifier to appreciate better power amplifiers, we'll study even this. Okay. So now let me draw the output characteristics of it. Okay. So how do you think this will look if I plot the load line here? If I plot VCE versus IC of this, how do you think this will look? What is the maximum value that this can take? What is the maximum value this point can take? I think all of you know how to draw the load line, correct? Let me call that as some DC voltage V. All of you know what is a load line?
Yes, ma'am.
Yeah. So what is the maximum voltage this can take? So I can write here this voltage V is equal to VCC minus ICRC. Correct? This voltage V is VCC minus ICRC. Right? So what is the maximum value we can take? Look at this equation and tell me, no?
CC.
VCC, right? That will be when IC is equal to 0. So maximum value we can, this is VCE, okay. Sorry. So maximum value we can take. V is nothing but VCE. Correct? Let me write this as VCE. So maximum value this VCE can take is when IC is equal to 0. When IC is equal to 0, the maximum value this is going to take is VCC. Correct? So what is the minimum value VCE can take? Theoretically, what is the minimum value it can take? Zero, right? So when will VCE be equal to 0? VCE will be equal to 0 when IC is equal to VCC by RC. So in this case, VCE is equal to 0. So VCE is equal to 0. At that point of time, the current is maximum, right? So this will be VCC by RC, correct? So if I have to draw the load line, then I'm going to join these two. And it's a straight line basically. Just a minute. Okay, more or less. So now, okay. So now, look at this load line. So when do you think the efficiency, where do you think that I should fix the Q point, the operating point of this, so that I get the maximum swing, output swing? So all of you know in an amplifier, you will have to bias this to operate in active region, right? For that, you will need some DC voltage here, VB. So VE is anyway 0. And then you will need some DC voltage here, VC. So this must be such that this is forward biased. And then the base the junction is reverse biased, right? And also generally, what do we keep this voltage, DC voltage here, so that you get the maximum swing? Okay, let us take one simple common source amplifier, okay? Since we learned it first, I assume that this will be much easier for you to relate. That's why. So now here we are going to give some DC voltage VG and some DC voltage VD so that this is operating in saturation. Correct? So that it can be used as an amplifier. Correct? No?
Yes, ma'am.
This you are able to understand. Okay. So now let us say VG is equal to, this is equal to 5 volts. Let us say this is equal to some 2 volts, 2.5 volts. Let us say VG is also equal to 2.5 volts. VD is also equal to 2.5 volts. And we have met all the conditions so that this operates in saturation. So now for this to behave like an amplifier, for amplification, what I do, I give a small voltage VG, I mean small input voltage AC signal, which is going to go above and below this DC voltage, right? Correct. So this will be the input signal. Correct.
Yes, ma'am.
Okay. So now how do you think the output will look like? It is inverted. The output signal will swing across VD. So this input signal will swing across VG. If VG is 2.5, this peak will be some 2.5 plus del V, and this peak will be 2.5 minus del V. Correct? Are
Yes,
you
ma'am.
all with me? Are
Yes,
you all
ma'am.
able to follow?
Yes, ma'am.
Okay. So now this VD is also a 2.5. So you'll get an amplified inverted signal. Correct? Something like this. Correct? So now this will be VD minus some gain times the input. This will be VD plus some gain times the input. This is going to swing across 2.5 volts, right? So now here at this point, the maximum voltage that this can take is 5. The minimum voltage that this can take is 0, theoretically. So if I keep this voltage here at 2.5, I get the maximum swing, plus 2.5 on top and minus 2.5 below, theoretically. Do you understand this? Are you
Yes,
all able to understand this?
yes, ma'am.
Huh. Now what happens if I put this at 3 volts? So this can only go up to 5. Therefore, the swing will be just plus or minus 2 volts, right? Because maximum it can go only up to 5. So if I make the DC voltage of this, which is the average of 5 and 0, then I get the maximum swing. Correct? Is this clear to all of you?
Yes, ma'am.
Can you all please reply in the chat box if it's clear? Only one or two are replying. Abhijit, is it clear? Abhijit S.
Yes, ma'am.
Shall we continue? Okay. Now similarly here, what should be the value of VCE so that you get the maximum swing? Apply the same concept. What should it be?
VCC minus 0 divided by 2.
Correct. So therefore, this should be equal to VCC by 2. Therefore, you have to fix the Q point here such that the DC voltage there must be VCC by 2. Similarly, at that time, what do you think will be the value of the current, IDC current? This will also be half, right? So it will be VCC by 2 RC, right? So if you have fixed the DC operating point here, so then you get a swing, full swing. While if you fix an operating point somewhere here, then what happens? Your swing is limited by the upper end, right? Your swing will be only this much. Correct? Similarly, if you have your operating point somewhere here, then what will happen to the swing? Swing is again limited by this, or low swing. So to get the maximum swing, you have to place the operating point exactly here in between. Correct? Now at this point where you're getting the maximum swing, let's calculate what is the efficiency. Now we are going to calculate what is the efficiency of a class A power amplifier. So can you recall what's the definition of this? How did you calculate efficiency in lab? So what's the definition of efficiency?
Power input by power output.
Correct. Which power? AC power or DC power? Anushka, can you tell me?
Ma'am, I think DC power. I'm not very sure.
Okay, let me remind you. So basically the definition itself says how much of DC power, how much of VCC is getting converted to output AC power. So therefore this is nothing but PAC at the output divided by PDC input power. Okay, this is the definition. So now this is the AC output. Now let's calculate the efficiency when the swing is maximum. Okay. So here you can see that the swing is maximum. So what's the peak to peak voltage of this? So V peak to peak here is nothing but VCC, right? Which means V peak is nothing but VCC by 2. And therefore what's VRMS? VCC by 2 root 2. Correct? So with this I can write PAC is equal to VRMS squared divided by RC. This is how you calculated AC output power even in lab, right? So PAC is equal to VRMS squared by RC, which is VCC squared by 8 RC. I mean, you substitute for VRMS here, from here, right? You substitute for VRMS from here. Now let's calculate what is PDC. So PDC is nothing but DC input power, which is VCC into IDC, correct? So now you know that this is IC in order to get the maximum efficiency. So therefore, this can be written as VCC into VCC by 2 RC, which is VCC squared by 2 RC. Correct? So now, let me call this 1 and this is 2. Efficiency is nothing but 1 over 2. This is nothing but just 25%. Right? If you just solve it, you will get efficiency to be equal to 25%. That too, this is the maximum efficiency of a class A amplifier. So when will you have the maximum efficiency? When you have the maximum swing. If the swing is less than VCC, then the efficiency of this amplifier decreases much more. Right? And intuitively, we saw why the efficiency of it is so less, because irrespective of whether there's a conversion or not, this amplifier is always on, which is not what we require, right? So that is why the efficiency is very, very less. We'll just summarize it again, and then I'll give you some time to note down. Okay, so this is basically a class A power amplifier. This is a simple common emitter amplifier. So we drew the load line here. We plotted VCE versus IC, and then we drew the load line. Okay, and then we saw that the point at which we get the maximum swing is when VCE, that is the DC voltage here, is at VCC by 2. And why are we looking for the point for the maximum swing? Because that's the point at which we get the highest efficiency in any power amplifier. So corresponding to this DC operating point is the DC current, which is VCC by 2RC. Okay. So therefore, the input AC power here is VCC into the current flowing through this amplifier IC. IC here is nothing but VCC by 2RC. Right? So therefore, we have the PDC, that is the total input DC power is VCC into VCC by 2RC, which is VCC square by 2RC. But what about the AC output power? That is the output RMS voltage square divided by RC. So during its maximum swing, we see that Vrms is equal to VCC by 2 root 2. Substituting that here, if you calculate the efficiency, you end up getting 25%, which means this is the maximum efficiency of a class A amplifier for any swing that is less than VCC peak to peak. You always end up getting an efficiency which is much lesser than 25%. That's why class A amplifier is hardly, power amplifier is hardly used. Sorry, you have an RB here. Okay, can you calculate RB so that the efficiency is maximum? So the first part of the question is, you have to calculate RB so as to get maximum efficiency. How do you do this? What should be the value of IC in order to get the maximum efficiency?
It should be less, ma'am.
VCC by 2R.
It should be VCC. Look at this. So the efficiency is maximum when the swing is maximum. For the swing to be maximum, IC must be equal to VCC by 2RC. Then only you get the maximum efficiency. Correct? So now calculate what is VCC by 2RC. This should be equal to the value of IC to get max. Correct? How much is this? How much is this value?
On 0.5.
Yeah. So this will be 0.5 amperes. So when IC is 0.5 amperes, what will be the value of IB? Correct? So now, can you calculate what should be the value of RB? So the voltage at this point is how much? One diode drop, right? So this is 0.7, correct? So now you calculate what should be the value of RB. You know IB now.
$772.
Correct. So RB should be 772 ohms. So in order to get the maximum efficiency, and how did we derive this? We started off with what should be the collector current in order to get the maximum efficiency, and from that as the base we calculated RB. Okay. So now suppose, okay, the next part of the question, okay. If IB, that is the base current, is 10 milliamperes peak, as in I give IB peak as 10 milliamperes. It's a sine wave basically, correct? So here I give a signal, a current signal. I mean, here I give a signal such that the AC signal here, current, is a sine wave, which looks something like this, with the peak value 10 milliamperes at this base. Okay, so this is your IP with 10 milliamperes peak. Okay. You have to find what is the AC output power and efficiency. Can you try to do this? Let's see. You already know what's the input DC power, right? So it will be 20 volts into IC, VCC into IC, where IC is how much? 0.5 amperes. Right? So you know what's the input DC power now. With this, you will have to, if I give a signal at the input such that IB peak is 10 milliamperes, you have to find the AC output power and the efficiency. So let me give you a hint. You can start with this. PAC is equal to I RMS squared at the output into RL. So we know that IB peak is equal to 10 milliamperes, right? So therefore we can find IC peak at the output is equal to beta into IB peak, which is 20 into 10 milliamperes, which is 200 milliamperes. This is the peak value of the output current, right? So now what is IRMS? That's nothing but I peak, which is 200 milliamperes, divided by root 2. Now substitute this back here. PAC is equal to now 200 milliamperes by root 2 the whole square into RL, which is 20 ohms. How much is this?
Point 4 watt.
Okay, so this is 0.4 watt. Now can you calculate what is the efficiency? So you all of you know what is PAC, no, which is 0.4 watt. What will be PDC? This will be VCC into IC. IC you know is 0.5 ampere. You know what is VCC, that's 20 volts. So VCC into IC is how much? What's the DC power? 10 watts.
Yes, ma'am. 10 watt.
Right? So DC power is 10 watts. So here you can see that the efficiency is just 4%. Right? So now what do you think is happening here? Even though you have fixed the Q point at the center, as in VCE and IC. So now here, this is your VCC load line. Now, this is VCC by RC. So you will have to fix your Q point somewhere here in order to get the maximum efficiency. No, we have fixed it. But here the problem is the input voltage that you're giving is such that the output voltage is not peak to peak. Even though you fixed your voltage at this point, the swing is not maximum. So what is the maximum swing that you can get here? So this is VCC by RC. No, how much is that? VCC is 20, RC is 20. So maximum is 1 here. So VCC here is 20, right? So now this is at 0.5. This is at 0.5. So the maximum peak that you can get here is 0.5 up and 0.5 down. So 500 milliamperes is the peak that you can get while you are having the peak amplitude of just 200 milliampere, right? Current. This is voltage. This is current. So therefore now you are having a peak current of only 200 milliampere, whereas this can tolerate a current of up to 500 milliamperes, and your efficiency will be maximum when you have a full swing. Here you don't have a full output current swing, and therefore the efficiency is less. It's not because of the Q point. Q point is fixed correctly, but your input current and the beta is such that your output current swing is not peak to peak. full 500 milliamperes. That's why. Is it clear? So therefore, your efficiency has reduced to just 4%. Now, think and answer this question, okay? So can I give the input current here? Can I give that to be equal to 250 milliampere? Can I give, instead of, I gave 10 milliampere here, no? Instead of this, what happens if I give IB is equal to 250 milliampere? Will I get a better efficiency? Does it work?
IC will be 5 ampere. Not 1.
So now IC peak to peak will be 250 milli into 20. That is 5 amperes. But can this circuit take a current of 5 amperes?
No.
No, right? The maximum that we have fixed DC current is only 0.5 amperes. So this circuit cannot take a current of 5 amperes peak to peak, and therefore the output will be distorted. So you don't get a good, I mean, there's no point of calculating efficiency when you cannot get the correct output voltage only, right? So therefore, your input voltage must be such that your output voltage is maximum, it can swing, not more than that. Now suppose your beta is 20, right? And the maximum swing possible is, current swing possible is 500 milliampere. So therefore, at the input IB can take a maximum value of 500 milli by 20. How much is this? 25 milli, right? 25 milliampere. So at this point, you get the maximum efficiency. If IB goes beyond 25 milliampere, then it forces IC to swing more and therefore get clipped. Therefore, you get a distorted output. If IB is less than 25 milliampere, just like the one we saw here, then we see that obviously the efficiency is much, much lower. Now let's take this example, okay? So now, these are very small voltages. Say you need, for this to operate in saturation, you need some voltage VGS minus VTH, which is say 1 volt. Okay. And for this to remain in saturation, VG must be equal to VD even after the swing, which is say, it is satisfied. Okay. So now here, in order to keep this MOSFET in saturation, we are talking in terms of 1 volts, 0.5 volts, 250 millivolts, and so on among, right? Whereas the swing that we are talking about in power amplifiers is 10 volt swing, 15 volt swing, 20 volt swing, 25 volt swing, which is much, much higher. Of course, in order to get the swing, we have to keep this in saturation. So even if you say you subtract, say, some 20 volts, you need 20 volt swing. Even if you do 20 volts minus some 1 volt, which is 19 volts, it's almost equal to 20 volts. So the amount of voltage that is required to keep this in saturation is much less when compared to the swing. Because here we are dealing with large signals. Is it clear?
Yes, ma'am.
Okay, now I'll give you a problem. You can try to solve this by yourself, okay? Okay, so you have to calculate input power, which is of course DC input power, B AC output power, and C efficiency of the amplifier. So you can take IB peak, that is the base current peak is 10 milliamperes. So what is IC? First, can you calculate IB, base current DC? Which will be 20 minus 0.7 divided by 1 kilo ohm, right? So which is correct, 19.3 milliamperes. So which gives us an ICQ of how much? Zero 0.48 milliamperes. That's not, this is nothing but beta times IB, no? Beta times IB. Okay. So now what will be PDC? This is nothing but VCC into ICQ. How much is that? 20 into 0.48 milliamperes. So how much is that?
It is 0.48 ampere.
Ha, right. Thank you. Yeah, he's right. So this will be 9.6 watts. Okay. So now let's calculate PAC. To calculate PAC, first we'll need what is IC peak, which is nothing but IB peak into beta. How much is that? 10 milli into 25, right? That's 250 milli. So this will be ICRMS squared RL, which is 250 milli is the peak, divided by root 2 is the RMS. So you square it into 20. How much do you get? 5 milli. 5 milli is too less, I think. It should be some 600 milli. How much is it? By 2. 0.625 milliwatts.
0.625 watt, not milli.
Okay. 0.625 watts. Correct. Why am I messing up with milli? This is 0.625 watts. Is it correct? I want the rest of you to verify. Are all of you on the same page?
Yes, ma'am.
Yes, ma'am.
Okay. So now calculate the efficiency. 6.5%. Yes. So basically we are expecting it to be less than 25% because we do not have the full input, full output voltage swing. Any doubts? So if you do not have any doubts in this, you can leave. If you have any doubts, please stay back. I'll answer it for you.